two supernovae, or sorry, the biggest stars actually explode relatively quickly and create type 2 supernovae, which explode primarily with things like the alpha elements. These are things like silicon and calcium and magnesium and oxygen and sulfur. And these elements are primarily formed in either hydrostatic burning or explosive burning in the type 2 supernovae, and then they're kind of dispersed into the interstellar medium. And so the first set of elements that you really get, other than iron, is of course these alpha elements. That's what the type 2 supernovae produce at very high quantities. And then that gas has been polluted by primarily these products, these alpha products. And what winds up happening then is the galaxy then, the gas that's been polluted creates a new generation of stars. That new generation of stars, continues through its life cycle, goes supernova, explodes, enriches the interstellar medium again with more alpha elements. And then at later times, about a gigayear or so later, type 1a start going off. And when that requires a white dwarf, when the type 1a start going off, you start getting the heavier elements, things like iron and iron peak elements, iron, nickel, cobalt, chromium, that kind of stuff. And then at even later times, you can actually get, the R process elements, the so-called R process elements, which come from, it's believed, some form of very explosive supernova or very energetic supernova explosions, as well as most recently neutron star mergers. So this is how you build up your elements over the course of how the universe evolves. You start with your alpha elements, you then move on to your iron and iron peak elements, you then move on to your even heavier elements. And again, this is sweeping a lot of stuff under the rug, but this is kind of a nice little cartoon picture. And so if we go back to that image of the Milky Way, we have this wonderful structure in the Milky Way. And one of the great things is that I've been able to build a group here at UT that works at the intersection of these various components. And so this is just a sampling of my group members just before COVID, or maybe a couple of months before COVID hit, and the so-called shark tank at UT. That's often called the shark tank because it has glass walls, but the grad students decided to put a shark in there because, why not? So this is my group. And some of the questions that my group tries to address in terms of the overall science questions are things like, how did the Milky Way come to be? And how did its different components form? So we know that it has a bulge, a disk, a halo, or potentially two disks, or probably two disks. So how do these different components form? I guess also, let's see here. Some of the other questions that I'm interested in are things like, what are the key physical processes that govern galaxy formation? What are the timescales involved in galaxy formation? How can we use stars as better tracers? And how can we improve the tools of galactic archaeology, things like chemical tagging, to answer some of these questions? These are a lot of questions, of course. And I only really have time in this particular talk to talk about, I'll talk a little bit about two of them. But what my plan is to give you I won't go into any very high level of detail about any one project that we're working on. My plan is to give you an idea of a smattering of some of the projects that we're working on. And the reason I'm planning on doing that is because I see these colloquia as an opportunity to form new collaborations and forge new collaborations. And so my goal is to give you an idea of what I work on and some of the projects that I'm working on. And I'd love to hear, of course, your input in areas in which we can collaborate. So one of the things that I like to tell students in terms of answering these questions and getting involved in galactic archaeology now is that we're kind of in this really wonderful period of galactic and stellar science, partly and largely because of these large spectroscopic and astrometric missions that are going on now that are producing very, very high quantities of very precise data for the positions, velocities, and chemical abundances for very large samples of stars. And so, we have these various smattering of, there's many more, but this is a very smattering of some of the surveys that I work with that are obtaining spectra for high resolution to low resolution spectra for, 250,000, 500,000 stars, and deriving 2025 elemental abundances for 100,000, 200,000, 500,000 stars at a time. And that's an incredible wealth of data with which now we can really piece together the galaxy. But then, of course, you have the Gaia spacecraft as well. And so Gaia is a European Space Agency mission. It's called the Billion Star Surveyor. It's the primary idea of Gaia is to produce the most precise 3D map of the galaxy by measuring parallaxes, proper motions, and positions on the sky for about 1 billion stars or so. They've also obtained radial velocities for tens of millions, so the brightest 10 or so million stars. And so this is something that the European community has been really interested in. And part of the reason why I went to Europe and to Cambridge to get my PhD was because I was very excited about the prospects of Gaia. And at the time, at least, in fact, this was back in 2013, there weren't very many US institutions that I knew of that were working on Gaia-related science or pre-Gaia-related science. And it was said that Gaia is going to revolutionize, galactic astronomy. And part of the reason is because, if you look at this image of the galaxy and you imagine that the sun is, located here. Now, the sun, of course, isn't really located there. This is a view of the Milky Way from the sun's position. But if the Milky Way were located here before Gaia, the precise information that we have is from this relatively local neighborhood, which really Hipparchus gave us. And when Gaia really expanded that from this small nearest 100,000 stars to a fairly large volume of a representative sample of something like 1 billion stars or so. And so with Gaia plus these large spectroscopic surveys together, we have we're in this really unique, extremely data-rich era to be doing galactic and stellar astronomy. And so Gaia has, I think, in some level, really started to revolutionize galactic and stellar astronomy. And every week I see, tens of new papers a week on Gaia-related science. To give you an idea of what we have now, so this is kind of what we have in this current data release. We're on the second data release of Gaia. We have positions and brightnesses for 1.6 billion stars. They meant to get 1 billion. They accidentally got 1.6 billion, so that's great. The mission cost about €1 billion, so it's about €1 per star, which is wonderful. We also have parallaxes for about 1.3 billion or so stars. And one of the awesome things about Gaia is the next data release, the early DR3, will actually be released December 3rd, 2020. So, mark your calendars for that. And the actual big DR3 release will be early 2022. One other really kind of personal note about Gaia is I actually rode, if you will, the Gaia wave through my career because I started my PhD in 2013 when Gaia was launched. I very explicitly remember this because all of the graduate students put a picture of Gaia on my desk when I came in for launch day and said, there was a little sticky note that attached to it saying, we hope Gaia doesn't blow up for your sake. So Gaia was launched in 2013. I became a postdoc in 2016 for the first data release. I became a faculty member in 2018 with the second data release. And so I usually joke with people and say, my goal is to try and get tenure by 2020, which is certainly not going to happen for the third data, or 2022 for the third data release, but not far off. I'll actually go up for tenure in 2023. One thing I do want to mention especially for the students in the room that may not have used Gaia before, we're often used to thinking about Gaia as parallaxes, which is what Gaia is measuring, as distance is the inverse of parallax. And so if you want to measure the distance to a star, you just invert the parallax and you're good to go. But because of the way error analysis works, you generally don't want to actually invert the parallax and try to get the distance. And the reason is because if the errors are roughly Gaussian in parallax space, when you invert the parallax, it's going to be non-Gaussian. You're going to get a kind of a long tail in distance space. And as a result of that, you'll wind up biasing your answer. So just be very careful when you're inverting parallaxes to get distances. Just a warning for people. Okay, so the rest of my talk will really be focused on, let's see here, keep an eye on the time. Yeah, the rest of my talk will really be focused on individual components of the galaxy and some of the work that my group is doing in those individual components. And again, the goal here isn't so much to give you an incredibly detailed rundown of what we did on any given project, but to give you an idea of some of the smattering of projects that we are doing in case you're interested in collaborating. And so we'll start out, I'm going to start out with the thin disk of the galaxies. That's the part of the galaxy that we live in. And the questions that I'm really interested in, the questions that I have been interested in the last couple of years in the galactic thin disk are things like, does chemical tagging in the galaxy work? And how can we use chemical tagging? What can we use chemical tagging for? And can we reconstruct the assembly history of the Milky Way through chemical tagging? And so I'll start out with that. And the idea of chemical tagging came around in the early 2000s from Bland Hawthorne and Freeman and Bland Hawthorne, 2002, I think. And the idea is pretty simple. It's that, imagine that you have these two gas clouds that have forming stars, and they're separated in different regions of the galaxy. And one molecular cloud is iron rich and the other one is iron poor. And they form their stars. And of course, over time, those stars interact with things and phase mix into the galaxy. And so they basically become jumbled up. Okay. And so the stars get jumbled up. And so the question is, can I determine where each star came from on the basis of its chemical fingerprint? And so if I take a spectrum of, star 1 and I take a spectrum of star 2, well, then I realize that, these two stars don't come from the same birth cloud because one is metal rich, the other is metal poor. But if I take a spectrum of these two stars and realize, oh, they have the exact same metallicity, and in fact, they have the exact same chemical abundances in all of the elements I study, then maybe they were born together. And so it's a really cool idea because one, if it works, right, then you can actually reassemble just measure the chemical composition of all the stars in the Milky Way, and you can reassemble where they came from. And therefore you can reassemble the entire history of the Milky Way. So it's a very powerful idea. And so I kind of, and the analogy I like to give in public talks is that this is like doing 23andMe DNA analysis for humans, but doing it on the stars. And so does this idea really work? Does chemical tagging really work? Well, this kind of really depends on answering the question. There's two underlying assumptions of chemical tagging. One is that stars born together have to be chemically homogeneous, and the other is that they have to be uniquely homogeneous from other things born elsewhere. So these are the two underlying assumptions. And so asking the question, does chemically tagging really work, depends on asking the question, are stars born together homogeneous or not chemically? And so you can answer that either yes or no. It's assumed to be yes for chemical tagging, but it's also assumed to be yes for things like exotic star characterization. So the way people, for example, measure the detailed abundances or even the metallicities of M dwarfs, up to now, people largely compare the M dwarf that's in a binary that has a binary companion with an FGK type, a much warmer star, because M stars are very cool, and doing the detailed chemistry of them is really hard because we don't really have a good handle on the molecular opacities there. And so exotic star characterization, whether it's white dwarfs or M dwarfs, rely on usually having a white dwarf and M dwarf in a binary pair with another star that's easier to analyze. And so that is assumed. It's assumed underlying assumption. The underlying assumption there is that stars born together are homogeneous. So if the answer to this is yes, then we're all good. Chemical tagging can work. Exotic star characterization works. And this is especially important for those people that are working on exoplanets, because I know a lot of exoplanet people are interested in looking at exoplanets around M dwarfs. And I love the phrase, know thy star, know thy planet. So you really want to understand the star that you're studying there. If the answer to this is no, well, then we might be in a little bit of trouble here, because then a lot of the things that we're currently doing won't really work. So this is a really important question. And so there was a nice work done by Siming Oh that tested this idea. And there was a test case here of Kronos and Krios, these two wide binary pairs. They were identified to be wide binary co-moving pairs, a co-moving pair in Gaia DR1. Then John Brewer had a nice catalog of abundances for them. And what they did was they went out and looked at the abundances for those stars. And if they were born together, well, the idea is that they should be the same chemically, right? And that means that, so you're seeing here the X/H ratio for the different elements from carbon to yttrium for the two stars, one in blue and one in red. So if they were chemically homogeneous, the blue and the red should be overlapping each other. But as you can see that they're not. There's actually a 0.2 dex difference in iron between these two stars, which is actually quite a large amount. And so, maybe chemical tagging doesn't work, because if we're finding wide binary pairs that are presumably born together that are really different in their chemistry, well, then that's a very serious problem. And so this is a really interesting and important question. And it's been, a lot of people have been studying this question of chemical tagging. There's a lot of, I've listed some of the references here, but I put dots before and after, because there really are quite a lot of survey, a lot of studies around this, because entire surveys are getting built around this concept of chemical tagging. And so when I arrived at UT, one of the things we thought we could do with funding from the Research Corporation was see if we can actually go out and see if this was more common. So we went out and we observed something like 25 wide binary pairs identified in Gaia DR2. We attained high resolution optical spectra from McDonald Observatory, which UT is a owner of. And we measured the chemistry of the two wide binary pairs. If the chemistry is alike, we're good to go. If they're not alike, well, then maybe we're confirming the Kronos and Krios result. So I took my grad students out to McDonald Observatory. We observed some of these stars. It was a great learning opportunity for them. And we wrote this paper. So this is work done with my grad student, Drea Carrillo, Maddie Lucy, and undergraduates, Megan and Dustin. And we wrote this paper basically looking at the identical and fraternal nature in terms of the chemistry of wide binaries identified in Gaia 2. And it turns out that in most cases, they turn out to be identical. I'll talk a little bit about, I'll show a couple of one or two plots of that, but in most cases, about 80% of the cases, we found that within the uncertainties, the stars, the twin wide binary twins, were chemically homogeneous at a level of about 0.05 dex. And I really like this question in part because I myself am a twin. So the media got a kick out of it because it's like twin astronomers studying twin stars, looking to see if they're identical or fraternal. Me and my twin, we're actually fraternal, but it turns out most twin stars seem to be identical. So we got high-res spectra, and then the kind of the more important plot. I'll skip over the spectra since and just show you the kind of the main plot of the paper. So what you're seeing here is this dispersion in the x over h ratio for all of the wide binaries in red triangles for each of the different elements that were studied, from carbon you're down to europium. And then you're also seeing in black circles is the typical uncertainty with which we think we can measure those particular elements. So if the black and the red are matched, then that means that within our uncertainties, we can't discern a difference in the chemistry between the two pairs. The orange triangles are random pairings of stars, random pairings of field stars, showing you that wide binaries are extraordinarily more homogeneous than their random pair counterparts. And in addition to that, in a lot of cases, the uncertainties are somewhere around what we expect in terms of the wide binaries are the level of dispersion that we're seeing in the abundances is roughly equivalent to the total uncertainty. In some cases, it's below, which probably means that we're probably underestimating our errors a little bit, or overestimating our errors a little bit, and we're doing a little bit better than we think. But we were pretty conservative in this particular work. My student Tyler Nelson has then expanded on that work in collaboration with Wan Sen Ting and Alex G. So this is showing again that difference in metallicity for our wide binary pairs as a function of the log separation of the pairs in AU. And the blue is the result that I had from my 2020 paper earlier this year. And Tyler has actually expanded that work to go into wide binaries that are separated by 10 to the 6, 10 to the 7 AU, which now you're starting to talk about parsec level. So these aren't really wide binaries more so than they are co-moving stars. And it turns out that somewhere right around a few parsecs, you start to see quite a large rise in the dispersion and the difference of the difference in metallicities. And so this tells us that right around in this area is right around when things stop becoming really homogeneous anymore. So at least what this tells us is that for the time being, chemical tagging may work. And the reason why I say it may work is because we only tested one assumption, which was this homogeneity assumption. We also need to test the uniqueness assumption. That's something that my group is working on now through looking at the doppelganger rate of stars across the Milky Way. But we haven't had any results there, so I don't have much to show. But now that we know that chemical tagging might work, well, what can we do with it, right? And so one of the things that I've been really interested in is hypervelocity stars. Some of the fastest stars in the galaxy. These are stars that are unbound, moving so fast, in fact, that they're unbound to the Milky Way. I actually got interested in this because of my work as an REU student with Adam Krause when I was a senior, going into my senior year as an undergraduate student. And it's one of what I did my REU on. And so I still work on that today, but now as a faculty member. And these hypervelocity stars are thought to be produced. The primary mechanism is called the Hills mechanism. And the idea is that you have you have a binary pair that has a triple body encounter with the a binary pair that has a triple body encounter between the binary and the supermassive black hole at the center of the galaxy. One star gets captured by the black hole, and the other one gets ejected at an enormously high velocity, about 1,000 or more kilometers per second. The stars that are thought to be captured are these so-called S stars, and the stars that get, flung out at extremely high velocities are the so-called hypervelocity stars. And the first discovery of one was, I think, in 2005-ish from Warren Brown. And then there's been a lot of discussions about, well, where the heck do these things come from? Do these things come from the galactic center? But if you orbit trace a lot of them, some of them don't look like they're coming from the galactic center at all. So I started beginning to approach this question. People up to this point had been approaching that question from a purely dynamical perspective. Let's do orbit integrations. Let's see if they get back to the galactic center. In 2018, I realized, well, I'm a galactic archaeologist. I primarily am interested in chemistry. We can approach this from a very different way. We can approach this by looking at the chemistry of the hypervelocity stars to see where they're coming from. And the reason is because there's been an argument going on as to whether these hypervelocity stars come from the center of our Milky Way, or if they're coming from the Large Magellanic Cloud, as work from Douglas Bourbeau. And so what I realized was, of course, the LMC has a very different chemical signature in this alpha metallicity plane. So this is alpha over iron on the y-axis. This is the average of the alpha elements divided by the amount of iron you have. Remember that the oldest stars will have lots of alpha and not very much iron. Younger stars will have not as much alpha and a lot more iron in general because of the type 2, type 1a time delays. And so the LMC looks something like this, whereas the bulge in the galactic center looks something like this in this alpha metallicity plane. And the most important point here is that if they're coming from the galactic center, hypervelocity stars should be drawn from this black line, whereas if they're coming from the LMC, they should be drawn from this gray line. And so you can use the chemistry of the star to actually test this idea. Where are these fastest stars coming from? So in collaboration with Rosie Wise, we went out and got high resolution spectra of just a handful of these, just as a proof of concept. Some of these fast moving stars, all the stars that we selected were actually just at the escape speed, not quite, they were just at the escape speed. So they had some uncertainty of being unbound versus bound. And it turns out that most of what we got, again, this is the disk pattern here. So the key plot here is the calcium or the magnesium plot. If these hypervelocity stars that we selected were coming from the galactic center, you'd expect them to be drawn from somewhere over here in this plot. If they were selected from the LMC, you'd expect them to be drawn from these orange dots here. And the black 5 points are the 5 stars that we were able to observe at the pilot project. And it turns out that all of them look like run-of-the-mill halo stars. And so we chemically tagged them to the stellar halo and not the LMC, which indicated maybe these fast-moving stars actually were just the fastest moving tail of the galactic halo. We have an ongoing project with an NSF grant to get many, many more. We've observed something like 40 now of these fast-moving stars, and we're now doing the analysis to see how many of them may have come from the LMC versus how many may come from the galactic center. So that's some of what we can do with chemical tagging. And I just want to talk very quickly about another project that we did earlier this year, looking at the chemical homogeneity argument again. Going back to restudy the chemical homogeneity argument, but instead of with wide binaries, studying it with stellar streams, very young stellar streams in the galactic disk. I got interested in this because I had some long conversations with Stella Offner and Adam Krauss at UT. We were talking about how stars form, whether they form in clusters or form along filaments and these long filaments. And the question was essentially, if they form along these long filaments, do you see any kind of chemical inhomogeneities because stars might be separated by tens or hundreds even of parsecs. And so we started looking for these young stellar streams, and luckily there was already some work out which showed that there were these very young streams being discovered in the galactic disk just by looking at, so these are just taking a sample of stars from Gaia DR2. They looked at the kinematics. This is VR as a function of V phi, VZ as a function of VR, and V phi as a function of VZ, so the 3 dimensions. And of course, there are these overdensities that appear, and this work from Meingast found that there was this overdensity, and they called this the Pisces-Eridanus stream. And what was really cool about it was a 200 parsec long stream. It had these clumps inside of it, and it was 400 parsecs. And in addition to that, if they do isochrone fitting, they find that the stream is something like about a gigayear or so old. And so was it born as if we were really interested? Was this thing born as a long 400 parsec stream? Was it sheared apart? Is it a cluster shearing apart? And what does the homogeneity of that thing look like? And so there was a, they did this, CMD fit to find that it was giga-year old, but then Jason Curtis went back and did rotation periods and found that actually this thing is not a giga-year, it's actually only 120 million years old, which makes it even more interesting because it's this 120 million year old, 400 parsec long stream. And what we're really interested in is, okay, is this thing homogeneous or not? And did it form together as homogeneous? So this is that particular cluster, and this is the Pleiades. So it's kind of like a Pleiades-like cluster. And so we went and got high resolution spectra again of this stellar stream. We find that it's chemically homogeneous to about 0.04 dex in metallicity. But what was really cool was that we were able to confirm the very young nature of the stream just using the lithium abundances. So this is again showing the lithium abundance as a function of temperature for the galactic disk, which is a few giga-years old. The Hyades, which is about 600 or so million years old, the Pleiades, which is about 120 million years old, and this Pisces-Eridanus stream in black. And so remember, lithium burns down over time in convective stars, and as a result, you can use it as an age indicator. And so this basically told us that this stream actually was in fact 120 million years old. I have a graduate student now, Catherine Manea, who's looking at many more streams and trying to understand, are all of these very long streams chemically homogeneous? Or to what degree do we see chemical inhomogeneity, especially in heavy elements in these streams? Okay, so that's the galactic disk. I'll talk very quickly. I think I have something like 12 minutes left. Is that right? 10, 12 minutes left?
You can probably go even a little longer than that.
Okay, cool. So I'll talk about the
15, 20.
Okay, cool. So I'll talk a little bit about the bulge, and then I'll wrap up with the galactic disk and some of the work we're doing with the galactic halo and some of the work we're doing in the galactic halo. So one of the really interesting questions that I have kind of come around to, my PhD was focused primarily on the stellar halo. My postdoc was focused primarily on the galactic disk. And towards the end of my postdoc, I started getting interested in working with Melissa Ness on the galactic bulge. And we were really looking for what the origins of the most metal poor stars in the bulge are. And the reason for that is because they are not only some of the oldest stars in the galaxy, but they can tell us a lot about how the bulge came to be. So our galactic bulge, we think is this kind of boxy peanut-like bulge. It's metal rich, ? We think it's probably mostly metal rich, but there is a metal poor tail to it. And that metal poor tail really hadn't been discussed so much. And there's been a couple of more studies here and there about the most metal poor stars in the bulge. This is just what the metallicity distribution of the bulge looks like in 3 different sight lines from the Argos survey from Melissa Ness's work. Melissa Ness found that there were these, multi-component, 5-component in the bulge, ranging from the most metal-rich stars all the way down to stars below metallicities of -1. So that's the 10th solar. And this is what I mean when I say metal poor, so about below -1. And it's those metal poor stars that we're really interested in. And part of the reason why we're interested in these metal poor stars in the center parts of the galaxy is because simulations seem to indicate that if you want to find the absolute oldest stars in the galaxy, you don't just want to look at the most metal poor stars. You want to look at the metal poor stars at the center of the galaxy. So this is based on a simulation work from Tomlinson, I think 2010, which is showing this. This is the Milky Way, and what you're seeing here, these numbers here, is the fraction of extremely metal poor stars that were born before Zia 15 in the simulations. And so you can see larger fractions of extreme metal poor stars that are the oldest stars, if you will, kind of being found in the central parts of the galaxy in the galactic bulge. So if you want to find the generation just before, or that just might have just come after population 3 stars to understand what population 3 stars are, you're going to want to look towards the center of the galaxy to find the absolute oldest stars, if you will, in terms of absolute age. And so studying these old metal poor stars, particularly in the galactic bulge, is really important because it can not only tell us about what the population 3 star look like, but also can tell us some information about how the Milky Way bulge came to be. Did it come from the disk? Did it come from accretion, and so forth? This is, of course, very difficult to do because the bulge is obscured by lots and lots of dust. It's also very difficult to do because the galactic bulge is primarily metal rich. So this is kind of a needle in a haystack kind of problem. But there's been a lot of work in the last 10 or so years on trying to find metal poor stars in the bulge. And I just listed just a couple of the surveys here. There's many more surveys that have started to do this, but of course this is really hard. And my student Maddie Lucy has actually been looking towards metal poor stars in the galactic bulge with Melissa Ness and I. We basically took a sample from a photometric sample from SkyMapper, and using SkyMapper photometry, we identified a sample of potentially metal poor stars. We got high resolution spectra from VLT UVES and kind of moderate-ish resolution spectra from VLT Giraffe, from the Giraffe instrument. And so Maddie is writing this PhD thesis really focused on looking at the chemical origins of these metal poor galactic bulge stars. She's actually published 2 of the 3 papers that are going to be in this series. The first one was on just looking at the UVES sample, the high resolution sample. I put the kind of the title and authors here in case you are interested in looking at that and getting more information about it. And our second paper just came out a couple of weeks ago about on looking at trying to study the dynamics of those stars and see which of those metal poor stars are halo interlopers versus which of those stars actually are contained inside, or I guess retained inside of the bulge throughout. But I'll just point out just 1 or 2 of the results from Maddie's work. And so what you're seeing here is a collection of abundances in X over Fe, so oxygen, sodium, magnesium, aluminum, silicon, calcium, vanadium, and copper as a function of iron for her metal poor bulge stars in black. The galactic disk in these kind of colors here, orange and blue or cyan. And then these kind of green circle or green triangles are the galactic halo. And so what she found very interestingly was that, number one, if you look at the calcium abundances, we were finding calcium abundances that were quite high, quite enriched compared to the typical run-of-the-mill halo star. And we were finding that in a lot of the elements, we were finding significantly lower dispersion and abundances for these metal poor bulge stars comparative to the galactic halo. Now, of course, this is a very small sample, so really anything to be concluded from this has to be taken with a grain of salt because we need a much larger sample. But this just shows you a little bit of how maybe the metal poor stars in the galactic bulge may intrinsically be a completely different population from the galactic halo itself. And so that's something that we're really interested in looking at. In addition to that, if we also looked at any kind of globular cluster chemical signature. So the globular clusters have this, not all, but some globular clusters display this really strange magnesium aluminum anti-correlation, where they find relatively low magnesium and relatively high aluminum abundances. This isn't seen in the galactic disk, which is kind of shown here in, again, orange and blue, and it really isn't seen in the galactic halo either. And what we find, at least in our sample, is not only that the aluminum abundances and magnesium abundances of our metal poor bulge stars don't necessarily match that of the galactic halo, we do find at least a couple of stars that seem to be, they could have come from globular clusters. And so some of those metal poor stars in the center of the galaxy may actually come from globular cluster disintegration. Although again, I caution that this, it's hard to make strong conclusions from any of this, largely because of course, there's only a handful of stars. There's only about 26, 27 stars in this particular sample. So the conclusion from some of this bulge work that we've been working on is that the bulge may be unique at some level from dwarf galaxies and from the stellar halo. Some percentage of the metal poor stars in the bulge may come from globular cluster disintegration. And we're expanding this survey now to include kinematics, which is COMS 2, that's currently out. And we've got about 600 stars now. Of course, I said we want more stars, and we have 600 stars, metal poor candidate stars observed with the Giraffe sample or with the Giraffe spectrograph, and we're currently in the process of analyzing those. So COMS 3, we think should come out sometime early next year or late this year. Okay, then I want to finally wrap up with kind of some of the work that my group is doing in the stellar halo and where I think galactic archaeology is going. I know that this is kind of, again, a hodgepodge and a mismatch of various things that I'm working on. But again, the goal here is to give you an idea of some of the stuff I'm working on, especially to spark any interest in collaborations. So some of the questions that we're interested in the galactic halo is where does the oldest, how does the whole old metal poor halo form? Particularly, what is the form of accretion? And is the halo dominated by one massive accretion event, or is it dominated by lots of small things coming into the galaxy? Just a quick reminder, we think that the Milky Way through lambda CDM comes about by basically by a process of galactic cannibalism, where you have galaxies that are creating from protogalaxies, which basically accrete and merge through gravity and you assemble your stellar, you build up your galaxy that way. Of course, you get these beautiful arcs and streams and tails and substructure, if you will, in the galactic halo in the simulations. We also see that in our own galaxy. But one of the really cool results to come out from all of this work was from Vasily Bulukarov and Amina Helmy's work, which showed the existence of a potentially single large, relatively massive system, LMC massive system, that may have come in and gotten accreted from the Milky Way. And so the way they found this, at least the way that Bulukarov et al. Found this, is by looking at the kinematics. So this is the V-phi, the rotational speed of stars, as a function of the radial speed, the VR of stars, in different metallicity bins. These are fairly metal rich. They're really metal poor, but they're metallicities between minus 1.3 and -1. And these are the most metal poor stars they have, between minus 2.3 and 0. And what Bulukarov found was that in this metallicity regime, in the galactic, nearish to the galactic plane, they find that you get this rotating group of material, and that's believed to be, it's rotating at a speed of 180 kilometers per second. It's got no preferred necessary direction in radial motion, and that was believed to be the galactic disk. Well, a signature of the galactic disk, right? It's a rotating group of stars. But they found this other group of stars, which didn't seem to have necessarily a strong preferred rotation, but was extremely radial. It had very, very radial orbits. And in addition to that, this is the reason why it's been dubbed in this particular paper the Gaia sausage, because it looks like a sausage in this particular space. And of course, as you go to lower and lower metallicities, that disk component goes away, and that sausage goes to being kind of this round, round structure. And so that's what this kind of structure is what they called the Gaia sausage. Around the same time, Amina Helmy found that if she looked at the energy and the angular momentum of stars, she found there was a group of stars that were I think they were relatively eccentric and highly energetic, counter-rotating. And these stars, if you look at when she looked at the chemistry, they tend to have chemistry that looks like what you'd expect for the LMC. But they were stars that were all over the galaxy, and they called this in their paper the Gaia Enceladus. And so people now talk about this as the Gaia Enceladus sausage, or the GES system. It's believed to be relatively old. It's believed to be about 10 gigayears old. It's believed to be alpha poor, which this alpha metallicity helps them derive a mass, and the mass indicated from that seems to be somewhere on the mass of the LMC. And interestingly, this is, chemically, it actually, if we look at we select those stars kinematically and look at the chemistry of those stars, as Ted Mackrick did in 2018, those stars seem to be very aluminum poor. This is data taken from the Apogee survey, and relatively magnesium poor as well. It's these kind of orange, bluish type stars. And I really like this figure because back in 2015, when I was a PhD student, I found these group of stars in Apogee that were very low aluminum, relatively low alpha. We didn't really know what they were. We just said they were accretion event material. But now with Gaia DR2, people were finding that this may actually be from a single LMC-sized system. And so I have a student, Drea, who's now following this up. And primarily, Drea is interested in looking at the S process elements. And that's because it's really hard to get S process elements, the heavier elements, from Apogee. It's just not possible. It's very difficult, at least in the infrared and the H band that they have. And so we've gone and selected a sample of stars from this Gaia Enceladus sausage system. We got high resolution optical spectra, primarily look at the S and R process elements. And the reason why we're interested in doing this is, of course, we're interested in understanding what the galactic chemical evolution of that Gaia Enceladus sausage system looks like. This is just showing plots from Drea where we were able to show that we can recover the temperature and metallicities that Apogee recovers from our optical spectra. So that's relatively good news between doing optical in spectroscopy versus infrared spectroscopy. And with the extra optical information, you're able to get detailed abundance information in terms of the neutron capture elements. And they look like what everyone else was finding back in 2010. So one of the conclusions from this work is the kind of this low alpha accreted material that Neeson and Schuster talked about in 2010 and other works we're talking about since 2010. That's likely what we now call the Gaia Enceladus cluster system. And we think that they're the same thing. And that's kind of shown here, where the Neeson and Schuster sample kind of overlaps with what we see the Gaia Enceladus sausage doing. And then finally, do I have any more time?
Yeah, maybe just a few minutes.
Okay, great. The last thing I want to talk about is this thing that I got interested in very, very recently, and that is, of course, we're really interested in the galactic halo. We're interested in looking at the detailed information in what we can find about the Gaia Enceladus cluster system. But one of the real challenges is that all of the surveys that we're looking at, whether it's Gaia or Apogee or Sloan or Lamos, they all have selection functions, and it becomes really challenging to make population level conclusions when you have selection function issues. And so there's a survey that I've been working with called the HETEX survey. It's the Hobby-Everly Telescope Dark Energy Experiment. And HETEX is an experiment primarily it's a completely unbiased survey using an IFU at the University of Texas, and it's measuring it's going to get 34,000 spectra per exposure. And the idea that HETEX has is really to use those spectra. They just point up the telescope, see whatever falls into the fiber, whatever falls in, they get a spectrum of. And they're looking for Lyman alpha emitters to understand how the universe and how dark energy has evolved over time. But what I realized is they actually have a lot of stars. They have hundreds of thousands of stars that just happen to fall in their fibers. And this is the kind of the fields that they're looking at out in the galactic plane. And because it's relatively unbiased, we can now get a relatively nice, this allows us to get a relatively unbiased view of the stellar halo. And that particular survey is great because of its design. The challenge, of course, with that survey is that HETEX is a very low resolution survey, resolution of about 750. And so in order to really do detailed information, we're really struggling to do it. And so this just shows you kind of where we are now with this survey, getting the HETEX Gaia value-added catalog. This is data that we just submitted to AppJ, showing you again the Gaia CMD with the HETEX spectra. And on the left panel, you're seeing the Gaia CMD and BPRP as a function of absolute magnitude. You've got your beautiful main sequence here, your turnoff, your subgiant branch, red clump, and white dwarfs. And if you just simply take some of those absolute magnitude color bins, you find these incredibly beautiful spectra as if it came out of a textbook, from the white dwarfs to the OBA stars, to the FGK stars, to the M and M dwarfs. And so we're now currently using these spectra to find metal poor stars. And what we're really interested in is finding, we're going to be doing not only full stellar parameter fitting with these spectra, but we're also now in a place now where I think we're able to study the Gaia Enceladus sausage system in a relatively unbiased way with this new HETEX survey that's just come out. So with that, I kind of want to end and just say that I think that my group works on all of the components in the Milky Way, and we're really interested in using the chemical composition of stars in the galaxy. And what I really hope to do at the end is put together a very detailed map of the galaxy, which I call chemical cartography, to put together a really detailed map of the galaxy where we place stars in that galaxy from Gaia, but then we color code those stars with their different chemical abundance signatures, going out and searching for the substructure that may exist in the galaxy. And so I'll leave you here with a video that I worked on with the Hayden Planetarium in New York City, where you can now go into the Hayden Planetarium in New York, and you can, this is in the foreground, you're seeing a simulation of the Milky Way. In the background, you're seeing individual stars placed in space by Gaia, color-coded by magnesium or iron from Apogee and Gaia surveys. And what I hope to do one day is actually build these large chemical maps of the galaxy, looking for how the galaxy is structured and using the chemical composition of those stars and the positions and motions to really piece together how galaxy formation came about. So I'll end there and open for questions.
Okay, thank you very much, Keith. So we have time for a few questions. So you can either type your question into the chat box, or you can ask to be unmuted. You can raise your hand. So I guess I'll start off, Keith. You talked a little bit about halo stars versus galactic center hypervelocity stars. My understanding is a lot of those are halo stars, like you said. But if you look at the really fastest ones, the ones that are more than 1,000 kilometers per second or so, I think a lot of those people think are from the Higgs mechanism, from a galactic center ejection. So the one, I'm just curious, the ones that you mentioned, how fast were they?
So that's a very good question. So these stars are moving at about 580 to about 600 kilometers per second. At the solar neighborhood, the local escape speed is somewhere about 538, depending on who you talk to, between 530 and 560 kilometers per second, depending on what the mass of the Milky Way is. Those 1,000 kilometer per second stars, most of them could probably be coming from the galactic center. The challenge with those stars is that, number one, getting detailed parallaxes for those stars has been really challenging. So doing 3D orbit integrations is challenging. And two, they're mostly O and B stars because of selection bias for how they were found. And it's very difficult to do chemistry on O and B stars. And so as a result of that, the question is still open as to whether or not they do come from the galactic center or not. There's a nice review from Warren Brown a couple of years ago, which kind of talks about some of these issues.
Okay, thanks.
Hi.
Oh,
Jim,
sorry, go ahead, Ashton.
Yeah, sorry, I only have a thumbs up. I don't have a raised hand for some reason, but I think a thumbs up is appropriate for Keith's talk.
I thought it was just ongoing applause.
I had a question about your magnesium and aluminum plot. You showed two different versions of this plot. One was from Apogee for the Gaia and Enceladus, but the one I had a question about was for the globular cluster, the hunt for globular cluster stars in the halo. Yes. So the dark green halo points are much lower than the light blue ones, and I assume this is because the halo stars were the aluminum was measured with the blue line, which has a huge negative NLTE, and the disk stars were measured with the redder doublet. But I was just wondering how that particular observational effect factors into the hunt for the possible globular cluster stars.
That's a very good question. So you're exactly correct. One of the challenges is of course that we don't account for, which we should in principle account for NLTE because these are metal poor giant stars. One of the things that we should do is see what the correction values are for those. Do you know offhand how large those corrections are? Because if they're at the level of 0.5 dex, then it won't really change too much the result.
It could be, yeah, the aluminum correction for the blue line can be like 0.8, 0.9 dex, depending on.
Yikes. Okay.
Yeah, it's huge.
Yeah, so we've talked a little bit to Maria Bergman and Karen Lind about doing these types of corrections. One of the things that I have struggled with is that one of the things that we're going to be doing actually for the next iteration of this is providing NLTE corrections for our values so that people can either use the NLT correction or not. When I talk to people, some people say the NLT corrections are just completely wrong, and some people say that you should trust them, and I never know what to really do there. So my plan is just to give the reader the option. And so we'll just report what the NLT corrections are, but that's a very good point. I should have a look and see what the NLT corrections are for those given lines.
It might be also just, report which liners are being used. Is it the doublet or is it the bluer line?
Yeah, that's a good point, yeah.
Okay, we have a question from Monsi.
Hi, Keith. That was great. I was curious how you overcome the resolution issue with the head-text data that you're playing with now. Since most of the other data sets are much higher resolution, do you use any, I don't know, AI or machine learning, or do you try to just work with very large samples? But I just
yes, That's a very good question. I didn't really have time to talk about it, but these spectra, even though to me, when I first saw this diagram, I was like, oh my God, this is amazing. These spectra are about a resolution of 750, which is much lower than what I'm used to using, which is R of 2000 up to like 100,000. And so the paper that we submitted really just scratches the surface of how we actually can utilize these spectra at much lower resolution to get metallicities. And the first this kind of exploratory paper that we did, we use a machine learning algorithm called TSNE, which I didn't talk about because I didn't really have time. But TSNE is basically T stochastic neighbor embedding. And the idea behind it is to project a high dimensional data set onto a two-dimensional manifold where things that are together, that are very close in that two-dimensional manifold, have spectra that look exactly alike. And things that are far away on that 2D manifold have spectra that look very, very different. And what we were able to do was apply TSNE to the HETEX data set, which is shown here. So every gray point is a HETEX spectrum. But what we did was we color-coded the spectra, we color-coded each point by its temperature in the top panel, its gravity, or its metallicity from a known higher resolution survey, either Sloan or Lamos. And interestingly, of course, all of the hot stars group up in one area, all the cool stars group up in an area. But what was really cool about this is that we found a region where there were an enormous number of metal poor stars all in one regime. And so this at least tells us that there is the information content is there in the spectrum or in the HETEX spectra to identify metal poor stars, which is how we would find, for example, the stellar halo. And in addition to that, there's a nice paper from Wunz and Ting a couple of years ago, which states that they basically just looked at what your precision in different abundances and metallicity would be if you went to lower and lower and lower resolution, from resolution of 100 all the way up to 100,000. And their results basically show that at resolution 700, you can do metallicities at the level of 0.1 dex, or even maybe potentially better. That was a completely theoretical study, but we're in a position now where we can test that with HETEX.
Great, thank you.
And that's a machine learning, I should say. That's a neural net they use to do that.
Okay. Any last questions? We have time, maybe one more. Are there any students who'd like to ask a question? Okay, I will ask the final question then, Keith. So you talked a little bit about stars with differences in composition, stars that are in binaries or co-moving pairs. So what's your opinion about the source of the difference in the composition? Because you have very accurate measurements, so you can reliably say that they're different. So
yeah, that's
I know there's a lot of literature about this, but I'm curious to hear your thoughts.
Yeah, there is a lot of literature, and in this particular paper, in the O paper, they primarily discussed the idea that this is planetary accretion, and their argument was, I think it's the refractories. I always get the refractories and volatiles mixed up, but I think it's the there's an enhancement primarily in the refractory elements that go into making planet cores, the rocky planet cores. And so if you accrete that material back onto your star, well, then your stellar atmosphere is now being enhanced by these particular refractory rocky material, basically. We looked for that signature. So there's a signature there that they expect, which is there's an enhancement in elements that have, I think, high condensation temperatures that are the refractory elements. So we looked for that signature in the 10% of stars or 20% of stars that we found that were not homogeneous. And what we found was that, that really only happened in one case or maybe two cases at most. And so is that a common effect? I don't know. I think that's a very good question that needs to be addressed. And it's something that we really need a large sample of wide binaries, a very statistical sample of wide binaries, in order to start addressing that particular question. Other mechanisms could be things like, atomic diffusion or radiative levitation, or other stellar effects in the atmosphere, or even chance alignment. So that's the other thing that we've been really interested in, is especially at these very, very wide separations, at parsec level separations, they could just be two stars passing in front of each other, and so you see them as co-moving, so you think they're wide binaries, and they're actually not. And so chance alignment is another possibility there, but that's very unlikely in low density field star environments. So I think the jury's still out on that. I can't really say that I have a strong weight on which mechanism it's going to turn out to be.
Okay, thank you so much, Keith. So we've run out of time, so thank you everybody for coming. Faculty